Hi students, how are we doing today? Oh good, I'm doing fine. I'm doing just spectacular. Great. All right. Now that we got that awkward moment past us, let's go ahead and start section 11.6. We're just going to do the first half of this section today, kind of just the straight algebraic problems. Our next lesson we'll get into some word problems using both logarithms and exponentials. So let's give this a shot. So we're going to solve logarithmic and exponential equations. So we're going to start with exponential equation. I'll call these facts. And I think we've seen some of these before. But if x and y are essentially the same number, then b to the x is going to equal b to the y. And that's not going to matter if x is positive or negative. That's nice. But number two, if x equals y, then the log base b of x equals the log base b of y, and those are b's down there on the logs, if and only if both x and y are positive. And the big reason behind why x and y are positive is because the domain of log of x is x such that x is greater than 0. That is, we cannot take logs of 0 or negative numbers. You could try it in your calculator, see what happens if you do log of 0. If you got the dollar store calculator, it might catch on fire. If you try the log of -3 on your calculator, it's also could be a possible fire hazard. Not as bad as dividing by 0, but you never know with some of these older electronics. Okay, I'm going to move on to the next slide. Hopefully you got all this. So these problems are all designed to be done with a calculator. If you don't have a calculator, you could leave your answers in terms of logs. But let's go ahead and see if we can solve this equation. I'm actually going to solve this one in two ways. One with, I know some of you with fancier graphing calculators can do different bases on their logarithms. And I'm going to go old school. If you don't have a fancy if you don't have a fancy calculator. Okay, so 4 to the x equals 20. So it helps to get an idea of what you think the solution is, maybe about what x would be. That's like 4 to what power equals 20? Well, we know 4 to the second power is 16. 4 to the third power is, you guys were supposed to answer that. 4 to the third power is, good, somebody got it, 64. So I'm pretty sure my answer should be somewhere between 2 and 3, and probably way closer to 2, since 20 is way closer to 16 than it is to 64. Alright, I'm going to solve this again in two ways. The way I want to get the x out of its exponential is I want to take the logarithm, and ideally I'd want to take the log of the same base, log base 4, because I have 4 to the x power. And what this essentially does, this is one of our special identities on the left side, is this whole side is just going to equal x. X. Gee. Sorry, stylist. Let's do that again. X equals log base 4 of 20. And now, if you have your calculator where you can enter the bases, like where you could do base 4, you could just put this answer straight in and get your answer. I unfortunately don't have that with me right now, so let me show you the second way of doing this. And what this pretty much does is it's going to use our change of base formula. In fact, just going on, if we remember the change of base formula does say that this should be log of 20. Okay, this is annoying. Come on. Gee. Divided by log of 4. That's what the change of base formula says. But let's go do the same problem here in a different color. I'll do this color. And this is going to be kind of using the change of base formula, but I wanted to show you how this works, because a lot of times this is useful. If I just take the log of both sides, that's base 10 in this case. If I just log both sides, if my stylus works, gee, man. Well, I can use the power rule on the left side here, since my x is as an exponent, and I could do log. So I have that x times log 4 equals log 20. Now if I divide each side by the log of 4, I get exactly what I had there on the left side. So if you actually see, it's a way of actually kind of deriving the change of base formula. Now I should be able to do this on my calculator. So I got 20 log divided by 4 log equals, there it is. Shouldn't matter which one you did this, and I'm going to put in approximately equals, since this is a decimal approximation, 2.161, and that should be my answer. And the nice thing is that if I wanted to, and you can do this, you can double check your answer. Put this back into x, so if I did 4 to the 2.16 power, it should be approximately 20. Again, we'll have a little bit of rounding error. Not too bad, right? So what if I wanted to solve something in terms of e? E to the 0.021x equals 120. Well, again, this is an exponential equation, so I'm going to need logarithms. I could tell it's an exponential equation because my x is in the exponent. So what I'll do is I'll log both sides, but since I have an e, I want to use a special log, right? Which log do I want to use? I heard someone in the back say it. Say it again. A little louder. Good, natural log. What? Nobody said that? Am I just imagining that somebody in the back of the class just gave me the answer? So I took the natural log of both sides. And why the natural log? Well, because that's base e. Okay, so I took the natural log here using the power rule. This gets to go out front. So it's 0.21x equals natural log of e equals natural log of 20. Question: what is the natural log of e? E to what power equals e? Good, that's just the identity. This is just 1. I didn't need to write that. So essentially, since I used the same base, that cancels. Let me put it this way: since I used the same base of logarithm as I had exponential, that essentially cancels that out, and anything out front gets to go out front. Like if it's just an x, then it's just an x, but in this case it's 0.021x, so we have 0.021x. Last step is I divide both sides by 0.021, and now I can go to my calculator and see what this is. Let's see here, so it's 120 natural log divided by 0.021, and hopefully my calculator worked alright. I had 227 I'll call it 98, and we'll stop right there. So that is, I'm going to have one more example of an exponential function. I'm switching slides right now. I like these problems. They're good. 2 to the x equals 3 to the x. This is kind of a double exponential problem. And if in this case, we have 2 to some power equals 3 to some power. So before we start solving this, let's maybe think of this graphically. I kind of have two exponential functions, 2 to the x, which will do something like this, and then I have 3 to the x, which will be similar. They should intersect somewhere and then go up faster. So my question is, where is that intersection point? Where do these two graphs meet? Well, let's try to solve this algebraically. And maybe you think you know what it is right now, but I can make these problems more difficult. And the way you want to solve this is, let's just kind of use my strategy from earlier, where let's just log both sides, and let's just log base 10 both sides. I can do that, why not? So this is base 10. Now I can use the power rule. That goes out front. Log 2 equals x log 3. Okay, how am I going to solve this one here? Well, both terms have an x. Let's just go to the side. And I know these logs can scare people, but how would I solve something like 2 to the x equals 3 to the x? Well, ideally I could subtract the 2 to the x to the other side, and okay, you know, we could subtract these two terms as well. So I'm going to do the same thing here. I'm going to switch colors. I'm going to subtract my x log 2 to the other side. And then, since both of these terms have an x, I can actually factor out an x. Okay, I know the left side is 0, and hopefully you could see that the answer is 0, but sometimes when these answers are more complicated, like the left side is 1 or something like that, the idea here is I want to just divide out whatever log 3 minus log 2 is to both sides. And in this case, just because I'm doing 0, x is equal to 0. This is what I was kind of mentioning. This one I would say is on the easier side, because these two indeed intersect at when x is 0, because 2 to the 0 power is 1 and 3 to the 0 power is what is 3 to the 0 power? Good, somebody said it. I know it's awkward talking to me when I'm in the video, but I'm in the classroom, you know. You can appease me. Alright. Solving log equations. So I put a little asterisk there to remind you, to undo a logarithm, you need to exponentiate both sides by the same base that your logarithm is in. That'll essentially undo the log. If you remember, we did our anti-log tables, so we took the log of a number in base 10, and then to undo it we had to raise it to the power of 10. That's what we called the anti-log. Same concept. Couple things to watch out for. That's negative logarithms. As I mentioned in the beginning of the video, we can't take the log of 0 or a negative number. And if we ever have two logs or more, we want to try to condense everything into one logarithm. So let's start with this problem. Smashing little problem. Log base 6 of 3x equals 2. Now, you might be thinking, I can expand that left side. I could do the log base 6 of 3 plus the log base 6 of x. And let me tell you, that's going to not be the correct strategy, even though it's not incorrect, because we want to always, the goal for these logarithmic equations is to have a log on one side, like we have now, and exponentiate both sides. So I can look at this two ways. I can just kind of go, hey, I'm just going to raise both sides to the 6th power, which may look a little confusing, but I'm going to go ahead and do it anyway. Now when I did this, remember we had this rule earlier that I said log base b, or b to the log base b of x equals x, and it kind of confused a lot of people, rightfully so, because it looks confusing. But still same idea here. Pretty much by raising both powers to the 6th power, exponentiating both sides, I've canceled out that logarithm. Another way to just kind of look at that is that we learned how to rewrite a logarithm like this. That is, we said 6 to what power equals this. So you could see here that's backwards, but that's 6 to the 2nd power equals 3x in this case. Lastly, just divide by 3, and I got that x equals 12. And again, you should double check your answers on these logarithms to watch for negative logs. So this would be the log of 3 times 12, and that's going to be the log base 6 of 36, which does in fact equal 2, because 6 to what power equals 36. You guys are so good. You knew that. This is too easy. I need to make this class more challenging. Okay, fine, I can do that. Let's do just a couple more equations and we'll call it a day. Alright, log base 2 of x plus log base 2 of x minus 2 equals 3. Okay, so what do I want to do here? What I want to do, I would love to exponentiate to undo a logarithm, in this case base 2. However, I want to make sure I have one log on each side. So let's use the property of logarithms that says if I'm adding 2 logs, that's the same as multiplying inside 1 log. Sorry, I needed a base 2 there. Equals 3. So now, if I raise both sides to the 2 power, again, that's going to undo my log on the left side. You don't have to write that step that I wrote before. You could just kind of just cancel the log as long as I raise the second side to the 2nd power. Sorry, the right side to the 2nd power. So now I got that x. Let's go ahead and factor this out, or expand here. X squared minus 2x equals 8. If I subtract that 8 to the other side, look at that, I got a quadratic. I could use the quadratic equation or see if it factors. Does this factor? Yeah, it does. In fact, I'm going to make this my last example because it works out nicely. Okay, so I have that x is going to equal 4, or x is going to equal, negative 2. And I'm done, right? Right? Yeah? No? Who said no? Who said no? Nobody said no. I said no. Somebody said no. No, I'm not done. I need to be just a little careful here because I have 2 answers, and I need to make sure I don't get any negative logs. I need to check it. Check it. That says check it, believe it or not. Check it. So if I put in 4 for x, I'd have log base 2 of 4 plus log base 2 of 4 minus 2, which is 2. And that should work. And in fact, I could even solve that. 2 to the 4th power is, I'm sorry, 2 to what power equals 4? That's 2. 2 to what power equals 1? 2 to what power equals 2? That's 1. So that works. But what about negative 2? So let's check negative 2. Log base 2 of negative 2. Ah, fire! Fire! So that time, that didn't work. We had an extraneous solution. So heads up, they're going to come up extraneous solutions. Watch for extraneous solutions. So in this case, my only answer is x equals 4. I think that's about enough for one lesson. What do you think? You want more? Yeah, hopefully you're going to get good at these. They're going to be useful, and next week we'll start some word problems, some interest rate problems, half-life, double-life, population type problems. I think you're going to love it. Okay guys, thank you.